Good morning, ladies and gentlemen. Today we are starting a new unit. It is called the Electromagnetic Induction, and what it focuses on is the exact opposite of what we did in the last unit. In the last unit, which was magnetism, we focused on getting magnetic fields from electricity. Now, as promised, we're going to start discussing getting electricity from magnetism. Okay, so now the focus is switched a little bit. So it starts us off with a prompt. Here we have a magnetic field, okay? And in it, you have a loop of wire, okay? In it, you have a loop of wire. The loop is currently rotating counterclockwise, okay? And it's a metal, it's copper wire. In the metal, electrons are free to move. And we also know that the magnetic field is going from right to left, okay? From the right to the left. What we want to know is in the right and left segments of the loop, will they be a force on the electrons? Okay, so what they're talking about is in this section right here, and then this section right here, is there going to be a force on the electrons? Okay, and if there is, in what direction is that force going to be? And in what direction will the electrons flow if the two wires from the ends are connected? Okay, and they are connected. So they're connected to something. So there is a flow. Okay. So if you remember the right-hand rule from the previous section for particles, what it said was to point your fingers in the direction of the field and point your thumb in the direction of travel. Okay. So this prompt wants us to look at these two segments right here, okay? And now I got to point something out. Right now, it says the segments are rotating counterclockwise. If the segments are rotating counterclockwise, let's focus on the right side right now. So we're looking at this one. In what direction is this end of the loop currently traveling in? At this point in time. So think of this as a Snapchat. It's traveling in a circle in circular motion. But right now, in what direction is the velocity of this segment? It is straight up, okay? It is straight up. That is the direction of this loop right now, rotating counterclockwise. This part of it is going up. So I want you to point your fingers to your middle finger, index, your ring, and your pinky. They should be pointing to your left, okay? And then point your thumb in the direction of the red arrow, which is straight up. So your fingers should be pointing to your left and your thumb should be pointing straight up. The back of your hand should be facing your screen right now, okay? And the back of your hand is the direction of the force on the electrons on the right, okay? Because remember, the right-hand rule says positive particles, it's out the palm. Negative particles, it's out the back of the hand. What flows in electricity is electrons. So we need to look at the negatively charged particles, which would be electron. So the force on the right segment, it is going into, think of it as going into your screen, right? Okay. So on this side, the electrons are currently going that way into the page. Okay. They're going that way. Okay. What about on the left side? Now let's look at the left segment. At the left segment, since this thing is rotating counterclockwise, this part of it is actually right now going straight down. Okay. The right side is coming up, the left side is going down. With the left side going down, do the same thing with your hand again. Your fingers should be pointed to your left, but now your thumb should be facing the floor. Your thumb should be pointing at the floor, and now the back of your hand should be facing you, okay? And that's the directions the electrons are flowing in, okay? So that means on this side, the electrons are coming this way, okay? And so to answer the question, in what direction is the force and is there a flow, what you have going on is you have the electrons flowing in this direction, coming out, and coming out on this end, okay? That is what's happening. That is what's taking place because of that direction. That all comes from the right-hand rule. All of that comes from the right-hand rule. And here's another example to prove that to you. So here we have a wire. Inside the wire, you have charged particles. The magnetic field is coming out of the page, okay? So take your hand and point your fingers towards you, okay? Take your hand and point your fingers towards you. Your thumb should be pointing in the direction of the red arrow, which is to the right, okay? So your thumb is pointed to your right, the fingers are pointed towards you, the back of your hand, should be facing the ceiling right now. That direction is where the electrons feel the force. So that's where they're going to flow, okay? Notice that the electron here is traveling upwards, okay? Because that's where it feels the force, okay? Because of the way this thing is moving, that is the flow. That is where the flow is going to take place, okay? This separates the charges, and the negative charges are going to move upward, which is going to produce a potential or a current, okay? That's where your voltages and currents come from. Okay, that's what that's referring to when it comes to a generator. So the same thing that happened here, if you know the direction, you can figure out the flow. We knew the direction here, we knew the velocity, the vector, and we figured out the flow. That's how they're connected. Okay? Electromagnetic induction is the process of creating a current or a flow of electricity by changing the magnetic flux in the loop, okay? So this is a fancy term, okay? This is a new term. So magnetic flux just refers to the flow of the magnetic field through an area, okay? So in the loop, notice how there's area in the loop. There's open space in the loop, okay? So magnetic flux, what magnetic flux is the how much of the field, this field right here, these arrows, how much of it goes through this area in a given amount of time. As this thing rotates, how much of it goes through that area can change, okay? It can change. So that's what magnetic flux is referring to, okay? You can get this by movement. So you can change the flux by moving the loop, which is what we normally do. You can rotate it. You can also generate electricity by moving the field. So instead of moving the wire, move the entire magnet, okay? Or you can also just either weaken the magnet or strengthen the magnet constantly. That'll produce a current, okay? So those are the three ways you can get current. You can get current from movement of the wire, movement of the magnet, or change of the field, okay? Those are the three ways you can produce electricity from magnetism, okay? If you do not have a change in the magnetic flux, if there is no change, meaning if there's no movement or if there's no adjustment to the field, there is no electricity being produced, okay? And the more movement you have, which in this case refers to the loop size, or the more you change the field strength, the more electricity you end up producing, okay? So there's this thing called Lenz's law. Lenz's law allows you to figure out the direction of the flow of electricity if you know the direction of the field, okay? If you know the direction of the field. What Lenz's law says is that the current will always flow in the direction opposing the field, okay? So if you remember from magnets, the way the field lines are drawn, it always comes out of north and into south, okay? Out of the north and into the south. That has a particular direction. Notice the direction of the arrows. They're pointing to the right here, okay? And because those arrows are going to the right, as you pass the magnet through the wire, so this time we're not moving the wire, we're moving the magnet. As you pass the magnet through the wire, notice the flow of the current is to the left. It is opposite of the arrows of the field lines, okay? it is always going to travel opposite of the magnetic field lines. And if you flip the magnet over and now you have the field lines going to the left, notice that the current is now going to the right. Okay, so Lenz's law, all Lenz's law states in simple terms, is that the flow of electricity will always go in the direction that opposes or that is opposite to the direction of the field lines. Okay, and there's a little simulation you can use to show this. Okay, so here I have my virtual magnet. Okay, here I have my virtual magnet. I'm going to turn on the field lines, and you can see that the field lines come out of the north. Okay, comes out of the north. As I pass it through, look at the voltage meter. You can see that the voltage meter activates, which means there is a flow of electricity. Okay, every time you pass the magnet through, you get a flow. And notice how no matter whether I pass from left to right or right to left, the voltage meter always starts with the negative portion first and then the positive portion second. But if I flip the magnet over, that actually changes. Now it goes from to positive first and then it goes to negative. All the positive and negative refer to is the direction of the current. Okay, so flipping the magnet over changes the direction of the current. And another thing the slides mentioned were the loops. The more loops you have, the more current you produce. Okay, the more loops you have, increased loop size, the more current you have. Here, on the bottom one, you have 1, 2, 3, you have 4 loops. At the top one, you only have 2 loops. Notice how when I pass the magnet at the one with 4 loops, the voltage meter goes all the way to the end on both sides, the positive and negative. But when I pass it through the smaller loop, that isn't necessarily the case. It doesn't go all the way down on either end. Because it has less loops, it produces less electricity. Okay, that's what this is. That's what that's showing. So the more loops you have, the more power you can produce. Okay, and now we can calculate how much current we produce with the following equation. Okay, so EMF. Okay, EMF is our voltage. Okay, this right here is another term for voltage. Okay, so this is going to be our voltage. So it has units of V. Okay, it's going to be V, units of V. V is for voltage. Okay, and what this says is that the voltage that you get is equal to the number of loops, which is N, times the magnetic flux. The magnetic flux is this equation right here. And I know you see the cosine and you see the angles and you might be getting a little nervous, but I'll take care of that right now. Okay. None of the problems that we are going to be dealing with are going to have any particular angles. We are going to assume that everything is under perfect conditions, which means perpendicular. So for our purposes, for our questions, you are not going to need the cosine piece of it because the angle is always going to be 0. And cosine of 0 is just 1. Okay? So for our purposes, you can ignore the cosine piece. Okay? So another way to have this equation is EMF is equal to negative N. And notice how there's this delta. I cannot get rid of this. What this means is change in. So this is the magnetic flux thing again. It says you have to have a change in the magnetic flux, which means you need to either be changing the field or be changing the loop somehow, some way. So this is the number of loops times the change in either the area or the field strength divided by how much time passed. Okay, I'm gonna write that in a different color because that's actually not that visible. I don't like using green. So again, you can ignore the cosine bit. Okay, and this is just the number of loops times the area times the magnetic field strength divided by time. Okay, this is change in time. Okay, and this is either change in area or change in the field. Okay, so this is the equation. This is the new equation we're going to be using. So this is the EMF equation. There's also one more equation, okay, that they don't put in here, but they should. So this is for voltage. This is for voltage. EMF is voltage. But if you want to calculate current, current and voltage are not the same thing. Current is your voltage, which is your EMF, divided by the resistance. Okay, and all wires have a resistance. But now we're talking about circuitry, and you're going to learn more about that as time passes. Okay, but these are the two new equations that go with this section so far. Okay, and we're going to apply it here so you can see where these numbers come from. So here we have a coil with 25 turns. This number right here, when they say turns, they are referring to N. So they just gave us N, okay? N is 25. A coil of wire with 25 turns is moving in a uniform magnetic field of 1.5 T. Remember the unit for magnetic field is Tesla. So they just gave us B. So now we have N and we have B. B is 1.5. The magnetic field is perpendicular. The reason they're telling you this piece is important. That tells us that that the angle is 0. And if the angle is 0, then that means that cosine is 1. Okay, that's what that is telling us. Okay. The cross-sectional area is 0.8 meters squared. Okay. The area, they just gave us A. Okay. So we have N, we have B, and we have A. And it says the coil exits the field in 1 second. So now we also have T. What are we looking for? We are looking for EMF. They gave us everything we need. So plug the numbers in. So EMF, okay, EMF, this is going to be equal to, and now remember there's a negative sign in front, it will be negative 25 times 0.8 times 1.5 divided by 1 second. Okay. Now this is technically, remember you need a change in something. So the wire itself is moving. Okay. It says the wire is moving in a uniform magnetic field. So the wire itself is moving. And it took 1 second to move. So the area didn't change and the field didn't change. Okay. But what happened is how long it was in there changed. So the delta T, okay, notice how this is a triangle T. That means you need to do a final minus initial. The final would be 1 second and the initial would be 0. So it would be 1 minus 0, which is still 1, which is where this comes from. Okay, so you plug all this into your calculator. Okay, 25 times 0.8 times 1.5, divide that by 1, and you get 30. Okay, this is equal to 30, which is what they got. Okay, they got, see this 3.0 times 10 to the negative, or times 10 to the 1, I'm sorry. And this is their voltage. This is their voltage. 3.0 times 10 to the 1 is 30. We just got 30. Okay, technically it's negative 30. I'm sorry. This should be a negative 30. Okay, and then if it says find the current, if the resistance is 1.5 ohms. So this symbol right here is the symbol for resistance. Okay, it means ohms. Okay, that's what that symbol means. And to find and to find the current, we need this equation. I is equal to EMF divided by R. So then I, therefore, has to be equal to 30 divided by 1.5. And if you do that, you do indeed get 20. Okay? And the unit for current is amps. Okay? And I'm sure you've heard that term before too. So you have voltage and you have amps. Okay? Voltage and amps. Amps is current, voltage, V is volts. Okay, and that's how you apply that equation. Okay, and that is the end for this segment. Okay, so the highlights: in order to produce electricity from magnetism, you need to either be moving a magnet past a wire, or you need to move a wire past the magnet, or you need to be adjusting either the area or the strength of the loop itself. Okay, those are the only ways you get electricity from magnetism. Okay, how are we on? Okay, we're at 20 minutes. Okay, so I will do one problem from today's work. So you have a 3-question worksheet that covers the induced EMF and current, and you also have a study guide section. It's only 3 questions as well. Okay, so this is your work for today. Okay, I'm actually going to cover this question here first. Okay, I'll do number 1 from here, and then I'll do number 1 from the study guide and call it a day. So what are we looking for in number 1? Let me zoom in just a tad bit. So in number 1, we are looking for time. How much time passes before the loop's area is reduced by half? So we are looking for t. So when we go to our equation, our EMF equation, which is a little below here, we need to get t by itself. We're looking for t. T is what we're trying to solve for, okay? So when you do that, when you get t by itself, you get that t is equal to, oops, I'm sorry, negative n times the change in either the area, or the field strength. This is a triangle. That's this piece right here is a triangle. Okay, that is a triangle. That is not a variable. Divided by EMF. So this is the equation we're going to be using to answer the question. Okay. So, do we have all the information we need? We want to know how much time passes when the area is reduced by half. So we know the area because they tell us that the pentagon covers an area of this much, and that the wire is the same area as the pentagon. Suppose a huge loop is placed on the ground, it covers the same area as the pentagon. So we have the area, okay? We know the field strength. It tells us the field strength is this, 6 times 10 to the negative 5. And we have the voltage. What about N? Does it tell us how many loops we have? That makes the world. Suppose a huge loop of wire. If the loop is pulled at opposite ends, the average. So it does not tell us how many loops we have. So we need to figure out. Hold up, I have to cover something really fast. Give me one moment. And we're back. My apologies. I had to go take care of something. So the problem does not tell us how many loops we have. But what it does say is it just says we have a huge loop, okay? So since it says we have a huge loop, I'm guessing that we are meant to assume that we only have one single loop, okay? Similar to the problem here. We just the one that we covered in the beginning here, okay, where you have one single loop, okay? Well, here's one single loop. So I'm guessing we just have one gigantic loop. That's what the problem wants us to think, okay? So we have A, we have B, and we have N, and we also have EMF. So we have everything we need to answer the question, okay? So now it's a matter of plugging the numbers in. So now, plugging the numbers in, let's do that. So we just assumed that N is 1, okay? So we have one single gigantic loop, okay? And this needs to be multiplied by our change in area or the field multiplied together. The field is not changing, so the field is constant. I'm going to write that out first, okay? The field is constant. It is constant at 6 times 10 to the negative 5 Tesla. Okay. Now the area is changing. Okay, the area is changing. The area in the beginning is this, 6.04 times 10 to the fifth. But it says we want to know how much time passes before the loop's area is reduced by half, okay? Because how they're producing electricity is by changing the area. It says so right here. The loop is pulled at opposite ends so that the area decreases, okay? And this will produce a current because you're changing something. You're changing the magnetic flux, okay? So then for change in area, it's your final. Your final is going to be half of this. If you divide that by 2, you get 3.02. So it is your final, which is 3.02 times 10 to the fifth. Okay. That is 10 to the fifth, correct? Yes. It's your final minus your initial. Your initial is what you had in the beginning. So this would be 6.04 times 10 to the fifth. And then you divide that whole thing by the voltage. And the voltage that we have is 0.8. Okay. So remember that one of these things has to change. Okay. In order for you to get electricity, either the area or the magnetic field has to be changing. Okay. One of these things has to be changing. Okay. And you can get that by either moving a wire through it, or I'm sorry, you can also have a change in time. But we want to know in this case when the area affects that. But one of these things has to be changing in order for you to produce electricity. In this case, it's the area that's changing, okay? So that's why the area, it's final minus initial. We want to know when half is gone. And then if you plug all these numbers into your calculator, I believe you end up getting something around 23, okay? Something around 23 if I remember correctly. But you plug those numbers into your calculator and you'll get your answer, okay? And that's for number 1. Number 2 and number 3 follow similar paths, okay? Just pay attention to the units, okay? And number 3, you have MV. M is mega. You have to go from mega back to regular, okay? So just remember you're paying attention to the units, all right? And that's for the worksheet. That's for that worksheet. Okay, now for the study guide just covers a little bit of the more conceptual stuff, okay? Number 1 wants you to figure out, using the right-hand rule, the direction of the flow, okay? And remember that circles, okay, when you see these dots, the dots mean out of the page, not into the page. If you see X's, that's into the page. Dots mean out of the page. So what you have is you have this square loop. We have a square loop traveling to the right. Okay, how are we on time? Okay, I want to try to end this around 30. You have a square loop traveling to the right. As it travels to the right, it ends up going in a field and then coming out of the field. Notice how the dots don't cover everything. It's a small little section. So what they're trying to tell you is that this is at time 1, time 2, time 3, so on and so forth. The loop is traveling through it. So at different times, they want us to write down where the flow is or how it's flowing around, okay? So at T1, are we in the field yet? The answer is no. At T1, we are not in the field. This is the field right here. At T1, we are not in the field. And if we're not in the field, we can't have a magnetic flux. And if you do not have a magnetic flux, you do not have flow. Okay? So there is no direction. So there is no flow here. Okay? There is no flow of electricity at this point. Okay? Now at T2, the right side, or side A, is now inside of the field. Where is the flow, or in what direction is the flow taking place? Okay, this is where you use the right hand rule. In what direction is the loop traveling in? The loop is traveling to the right. That's where your thumb points. So your thumb should be pointing to the right, okay? And then your fingers should be pointing in the direction of the field, which is out of the page. So your fingers should be pointing towards you, and the thumb should be pointing to the right. And the back of your hand should be facing the ceiling right now, okay? Fingers towards you, thumb to the right. The back of your hand should be facing the ceiling. And that is where the electrons are going to flow, okay? So that means the electrons are flowing up, okay? So at T2 for side A, the direction of flow is up, okay? I'm going to use arrows instead, okay? The direction of flow is up, just for space, okay? If it's going up at side A, what's it going to do to the electrons on side B? It's going to push them to the left, because if I'm shoving up to this side, in order to make up for it, I need to make room. I need to push the ones over here to the left, okay? Since that area is now crowding up. So it's going to go left here. At side C, what's happening, since B is coming to the left, this has to be going down. And then at side D, you're going to the right, okay? So it's up, left, down, right, okay? At side A, B, C, and D. That's what's happening. What about at T3? What's happening at T3? At T3, the entire loop is inside the field now. And if the whole thing is inside the field, guess what happens? The right side, you have electrons that want to come up, and on the left side, you have electrons that want to come up. If you follow the right-hand rule, on the left side of the loop and on the right side of the loop, you're going to have electrons that want to go up. And if they want to go up on both sides, they get blocked, because this side is going to be pushing the electrons this way, and this side is going to be pushing the electrons this way. So you get complete cancellation. So when the whole thing's inside, you do not have flow. Okay. T4. At T4, you have the opposite of T2. At T4, only the left side is inside the field. And if that's the case, then you're going to have flow going up on this side only, which is going to push this to the right, which is going to push this down, which is going to push this to the left, okay? So A, instead, it's going to be the exact opposite of T2. So at A, you have down. At B, you have right. At C, you have up. And at D, you have to the left. And then at T5, you are completely out of the field again, which means, once again, you have no flow. Okay? I hope you guys are getting more comfortable using the right-hand rule. Okay? This is where you would apply it. 2, you can figure out from number 1, and then 3 is just another example of using the equation. Okay? So this is what you're going to be doing for today. 2 equations to apply. You have the EMF equation, and you have the current equation. Okay, these are your 2 equations. Remember, you can ignore the cosine. Don't let the cosine piece scare you. Okay, these are your 2 equations you're using for today and the 2 concepts. All right. If you guys have any questions, as always, please feel free to reach out. Hope you guys are doing okay. Have a happy Monday. Enjoy the rest of your day.